All right, in this video, we're going to complete these 4 pages about periodic functions that we skipped earlier. So we think about periodic functions as trigonometric functions, sine of x, cosine of x, but there are other periodic functions too, and we've got a few mentioned here. We're going to see one example like a saw function. There are other functions that are periodic but aren't necessarily trigonometric. So the definition for periodic that we're going to use here is that a function is periodic if there's some non-zero real number, so that f of t plus whatever that is equals f of t. So if you move t future, like this capital T future, into the future, you'll get exactly the same result. Or if t is negative, if you move backward, then you get exactly the same result. So that's what it means to be periodic. The smallest positive number is called the fundamental period. So like for sine of x, that would be 2 pi. All right, so now kind of understanding that, let's look at this, look at that definition in the context here. So we're going to show that this is periodic with period capital T equals 2 pi. So we've got sine of t plus 2 pi. We want to show that this is equal to the sine of t, no matter what t is. So one way to do this is to use the identity for the sine of the addition of 2 angles. So this is sine of t cosine of 2 pi plus cosine of t sine of 2 pi. So that's sine of t times 1 cosine of t times 0, and so you get sine of t. Should note here, this doesn't prove that this is the fundamental period. It only proves that the sine function is periodic. All we've shown is if we add 2 pi, we'll get the same result no matter where we start. But it doesn't. This is not a proof that 2 pi is the smallest. So we got to be careful here. This is not a proof that it's the fundamental period. All right. So translating, what happens when we translate here? That what if we translate more than 1? So we're going to assume that f of t is a periodic function. It has a period capital T. Now for all t in the domain, we can actually, if you can add 1 t and get the same result, well then couldn't you add 2 and get the same result, or 4 or 5 or negative 7? And so that is actually a theorem here. And it's I hope that's intuitive. I'm going to do a kind of a brief proof, not a full proof. You can do a proof by induction here, but it's basically what I was just hinting at. So we know f of t plus capital T is equal to f of t by definition because it's periodic. Right? So we know that's definitely true. So this should be true for any t, right? And so if this is true for any t, shouldn't it be true for, say, t plus the capital T? Right? Shouldn't that also be true? Right? This is an example of a t in the domain. And so this should also be true. So that's f of t plus 2t. And you can repeat this process over and over and over. If you repeat it n minus 2 times, so 1 less than the n there. So if you repeat it n minus 2 times, that would be f of t plus n t. And so you get this proof. Now this is, again, this is a little casual here. This isn't a full-on proof, but just kind of hinting at the idea here, why this is true. Now one thing that this really points out then is that a periodic function can't have a finite length. Right, because this n can be any integer. So because there's no limit to that, you can't have a finite length to this particular one. Now you could, so notice this says for all t in the domain, you could start at 0 to infinity or 0 to negative infinity, but you can't have a finite length. All right, so here's a particular example of a non-trigonometric periodic function. This is a triangular wave function. We're going to try to express this function using some step and window functions. So because this is periodic, right? It's repeating itself here, here, here. We really only need to define it over a single period. And so I'm just going to use this period right here because then it repeats itself after that. So f of t, it's a piecewise function, right? It's the line at t from 0 up to, we'll say, well, we could include 1 or not, doesn't matter. The next one is a slope -1. It would have a y-intercept at 2, so that's 2 minus t. We'll stop at 2 here. Again, we can start over, but since we included the 0 here, we'll leave the 2 to be included for the next one. So that's our piecewise function for this, and then it's periodic. It would just repeat itself after that. So if we're going to write this now, let's use our unit step functions and our window functions. So if we're using our unit step functions, think of, we'll turn the t function on at 0, and then turn it off at 1. And then we'll turn on the 2 minus t function at 1, and then subtract it back out at 2. Right? We could also use the window function, this on-off, and so we can turn on the t function between 0 and 1, and then turn on the 2 minus t function from 1 to 2. And so now, in order to get all of this, what we do is we just note this has a period of 2. And now with that additional comment, now we've included all of it, not just that particular window. So if it repeats itself, we give a definition here, and then we note its period. All right. So what we just did is we actually did something called the fundamental window. That if I know that window, then I have the whole function because it's periodic. So we're going to give that definition next. So we're going to assume that this, or let f of t be a periodic function with period capital T, then the function. Now we're going to put a little subscript. It's f of t between 0 and its period, and it's 0 otherwise, everywhere else. And that's called the fundamental window. Now we can do this with the window function as well. So we can say, all right, well, this is f of t turned on at t. I guess we should put a 0. It should be included here, right? So it's f of t turned on at 0, and then subtracted, turning it off at that capital T, that period. And so you could use the window function as well. And so this, again, this is called the fundamental window. That's that first window. Like you can do from 0 to 2 pi. You can think of that from sine and cosine, and then you just repeat it, right? That's the fundamental window of those functions. All right, well, how do we compute the Laplace transform when we have this fundamental window? Fundamental window. All right, so we have a new type of function. How do we compute the Laplace transform? Let's use the definition, right? So it'd be 0 to infinity e to the negative st, and then this fundamental window dt. Now the fundamental window is 0 to t. Between 0 and t, it's just a function. And then after that, I mean, let me do it this way. We'll split it up. We'll do 0 to t of the fundamental function, and then t to infinity of the fundamental. There we go. All right. So splitting up 0 to t, t to infinity. Between 0 and t, right, in the fundamental window, it's just that f of t, and then everywhere else it's 0. So this one is 0, and we just get the integral from 0 to t, e to the negative st, f. No fundamental window notation here because we're only going from 0 to the period, so we're good. All right. So let's talk a little bit more about this. We need a little more theory, and then we'll be able to actually compute a Laplace transform of a periodic function, the one that we did earlier, that like triangular wave problem. So instead of giving this up here, let me do the proof that like a derivation, and then we'll fill this in and you'll see how it works. So capital F here, so the Laplace transform of that fundamental window. The fundamental window we can use with the unit step function. So this is the Laplace transform of f of t in the unit step function minus turning it back off, right, with the unit step function at that period, capital T. And so we can take the Laplace transform of these two separately. And then the unit step function turns on at 1, and the Laplace transform turns on at 0. The Laplace transform is going to go from 0 to infinity. So this is just the Laplace transform of that f of t. And here I'm going to note that this is a periodic function, and it's periodic for multiples of that period. So I'd like for these to match so we can use our unit step function, right? So, but it should, right? It will, because it's periodic. So those will be equal. All I'm doing is just replacing that because it's periodic. If I move back one period, that'll be the same value because it's periodic. So this is the Laplace transform. Like usual, that's just the notation for the Laplace transform of that f of t function. And this one has the unit step function. This is the one we just learned. So this is e to the minus s, and then it's that period times the Laplace transform. So you get the Laplace transform times this kind of interesting factor 1 minus e to the negative s times that period. And so if we solve for the Laplace transform then of this function, we get the Laplace transform of the fundamental function over 1 minus e to the negative s t. All right, let's try this last example then, where we're actually going to do the Laplace transform of a periodic function, and we're going to use this theorem to do it. All right, so we're going to compute the Laplace transform. Let me put that fundamental window back in here. It's t from 0 up to 1, and we'll write it negative t plus 2 from 1 to 2. And let's see, let's write this using some unit step functions. So t times the unit step function, turn that one on, and then subtract, turning it off at t minus 1. And then we've got turning this one on, negative t plus 2, turning it on at 1, and then subtract. We'll turn it back off at 2. Let's combine these middle two ones together so we don't have these multiple step functions. So let's see, that'll be, how do I want to do this? Let's do it this way, plus for now, negative t, so negative 2t plus 2 times the t minus 1 unit step function, and then we have minus negative t plus 2 times that unit step function. Now, if we're going to take the Laplace transform, we've got these unit step functions. It would be nice if this was some function g of t minus 1. Actually, it wouldn't be nice. It's necessary. In order to take the Laplace transform, we need this to be a function of t minus 1, and we need this one to be some function h of t minus 2. So if we just do a little reconfiguring here, we want this to be t minus 1. You can see if we factor out a negative 2, we get t minus 1, u of t minus 1. And then here, if we factor out a negative 1, this ends up being plus t minus 2, u at t minus 2. And so now these match the step function. All right, so now we're ready to take the Laplace transform. I think I'm going to move over to the next page. So let's recopy our fundamental window. T times u of t, and then minus 2 times t minus 1, u at t minus 1, and then plus t minus 2, u at t minus 2. So the Laplace transform of that fundamental window would be, let's see, it would be the Laplace transform of t u of t minus 2 times the Laplace transform of t minus 1 u at t minus 1 plus the Laplace transform of t minus 2 times u at t u of t minus 2. Whoa, got the color a little screwy there. Oh, there we go. All right. So the unit step function, again, turns on at 0. The Laplace transform is integral from 0 to infinity. So this is just the Laplace transform of t. Here we have a little shift, right? So this is going to be our e to the negative s times 1 times the Laplace transform of just t. And then here, this will be plus e to the negative s times 2, again, times the Laplace transform of t. All right, so this is essentially in the t spot, but it's been shifted, and so because it's been shifted here by the unit step function, we have this e to the negative s times, I think we were using a for that particular variable. All right, well, this is 1 over s squared minus 2e to the negative s over s squared plus e to the negative 2s over s squared. So conveniently, that's 1 minus 2e to the negative s plus e to the negative 2s all over s squared. And so looking back at our theorem, the Laplace transform is the Laplace transform of the fundamental window divided by 1 minus e to the negative st. So this implies that the Laplace transform of this wave function, the full function, is the Laplace transform of the fundamental window over 1 minus e to the negative st. So that's 1 minus 2e to the negative s plus e to the negative 2s all over s squared times 1 minus e to the negative, let's see here, I guess we know what the t is, do we not? I didn't actually have that in my notes, but if we go back, the fundamental period is 2. So we can write 2s right there. Ooh, I wonder if we could go further. Can we factor that? Oh, I think we can. I'm just going to leave it that way for now. That's good enough, but I think we can factor that. Maybe not. I don't have to think about it. I think it might be factorable, but we'll leave it like this for now. This is good enough. So that's the key there, that you find the Laplace transform of the fundamental window with all those step functions in there. And then the Laplace transform of your function that you're looking for is the Laplace transform of the fundamental window divided by 1 minus e to the negative s times its fundamental period, that smallest t value where it repeats. And so that is it. That should give you enough information to complete the little quiz that we're going to do at home.
A few moments later.
All right, you know what? This is going to bother me. You can actually factor this. It bothers me to leave it the same. So in the numerator here, this is actually 1 minus e to the negative s squared, right? Because 1 minus e to the negative s, 1 minus e to the negative s, you have a 1, a negative e to the negative s, a negative e to the negative s, and then a positive e to the negative, and then you add those, negative 2s. And then the denominator, this is a difference of squares, 1 minus e to the negative s, 1 plus e to the negative s. So that one does not have a middle term, but it's subtraction, and then again you add those exponents, and so you actually can get a simplified version, 1 minus e to the negative s over s squared times 1 plus e to the negative s. All right. Does it feel better now that you simplified that? Okay.